Hi class, this is an example problem for Unit 8.1. And in Unit 8, we're talking about friction and particularly static friction. And so in this problem, we're going to work through um, a simple problem that goes through some of these concepts of impending motion and static friction and finding, in this case, when something will slip. So what we have here, this is problem 8.5 from the 13th edition of the book. We have a wall and there's a ladder leaned up against the wall. The ladder is 15 feet long, and at each point of contact, there is a coefficient of static friction given. We are told the ladder weighs 80 pounds, and at point A, the coefficient of friction is 0.4, and at least for the first part of the problem, we're going to assume that the angle that the ladder makes with the ground is 60 degrees. So we're going to do two different problems with the same ladder. In the first part, the simpler part, we're going to determine if the ladder will slip, assuming point B is smooth, or in other words, that the coefficient of static friction at point B is 0. And then in the second part, we're going to change it up a little bit and say, assuming that the coefficient of static friction at point B is instead 0.4, then what is the smallest angle that theta can be at which the ladder will not slip? So we're going to do part A first. So I'm going to just redraw this as a free body diagram, as we've been doing so much lately. So if I were to redraw this as a free body diagram, I'm going to have this my ladder. I'm going to have my weight acting at the middle, of 80 pounds. And then we're going to have a normal force at point A, and the friction. So we'll call that NA. I'm going to call this force friction A. And then we're going to have a normal force at the wall that we'll call Bx, and there is no friction force at point B in part A because we're assuming that it's totally smooth. So we have the setup, we have three unknowns, and all we're going to try to find, so the way this problem is worded, we're trying to find out if the ladder will slip. And so at the point, that means we're dealing with what we call impending motion. And when we're dealing with impending motion, we're going to assume, therefore, that the friction force at A is equal to NA times mu sub A. Now this is the maximum that the friction force can be, is the normal force and times the coefficient of friction. The friction force can be less than this, but it cannot be greater than this. If it has to be greater than that to maintain equilibrium, then we'll have slip. So we're going to assume that because we're finding the point at which it will slip, that this is the, or rather, let's say it this way. Let's say that rather than saying that's what we're going to call it, we're going to say that we know that the friction force max, maybe we should word it that way. The maximum is this. And so what we're going to do is we're going to find the friction force that it actually is to maintain equilibrium. And if it's less than the maximum friction force, then we'll say it won't slip. If the friction force here is greater than what the maximum can be, then we're going to say it slips. So sorry if that was a little misleading. So let's start with our sum of forces in y, because that's a pretty simple problem. Sum of forces in y have to equal 0, and that's just going to be NA minus 80. So we know NA must equal 80. Simple enough. Now let's look at the sum of, so knowing this, that means that therefore the friction force max is 80 times 0.4, which is going to be 32. So that's sort of our magic number. If the friction force is greater than 32, it's slipping. If it's less, it won't slip. So now we're going to look at the sum of the moments at point B because we're interested in finding the friction force. So we'll do sum of the moments about point B equals 0. And what that gets us is we have 80 And that moment arm is, that distance is 7.5. So times 7.5, and we have to do cosine 60 to get the horizontal throw, or the horizontal moment arm for that. And that's going to be by right hand rule positive. And then we're going to say, okay, the moment caused by the friction force, that's also going to be positive. So let's throw a positive sign there. So plus friction force A, and that length, that vertical distance, is going to be 15. That's the length of the ladder, times sine of 60. All right, now we just have NA, which is going to cause a negative moment. So minus NA, which we know is 80, minus 80 times 15 cosine 60, because that will give us the horizontal distance, the horizontal moment arm. And when we do all the math, we end up, so let's do just a couple steps of math. We get 0 equals, that comes out to 300 plus 12.99 friction force A minus 600. And when we do that math, we end up getting that friction force A is going to equal 23.09 pounds. Therefore, no slip, right? Because 23 is less than the maximum friction force. We know that it will not slip. So part A, no slip. Now let's look at part B. Part B is going to be a bit more tricky, and it takes a little bit of kind of thinking properly about. So in part B, the free body diagram is going to look a little bit different, because we will now have a friction force B, right? Because now we have now we're not assuming smooth anymore. Now we're assuming that UB equals 4. So what we are going to find right now, we're finding the angle that will cause it to be right at the point of impending motion. Now to do that, this is a little bit tricky to think about, but the assumption you have to make is that you can't just be slipping at one of these points, right? For the thing to be at the point of slipping, both points have to be slipping, right? You can't be slipping here and not slipping there, otherwise you're not moving, right? If you're slipping here, then you're slipping there at point A and at point B. So we are going to assume that friction force A equals NA mu sub A, and friction force B equals NB mu sub B. So that's the assumption. It has to be slipping at both points or slipping at no points, right? It's not going to just slip at one. So let's take a look at this. So let's start with the sum of the forces in Y again. Sum of the forces in Y equals 0, which equals NA plus friction force B minus 80. So we can rearrange that and get that 80 equals, right, and we can substitute this in, so we can say 80 equals NA plus NB mu sub B. And let's just keep that in our back pocket for a minute. We'll come back to that equation in just a second. So now let's look at the sum of the forces in X. Sum of forces in X equals 0. And that in X we have friction force A minus Bx. And so we know, and so if we substitute in what we had before, we know that NA mu sub A equals B of X. call that 2. Sorry, I'm being inconsistent with what I'm calling things. I called, let me be consistent with what I'm calling things. Let's call that NB. Not being consistent with my terms. Instead of BX, I'm going to call it NB to just be a little bit more consistent. So we have this relationship. So let's sub in this value for NB into equation 1. So we're going to say subbing equation 2 into equation 1. We get 80 equals NA plus NA mu sub A mu sub B. And so when you do all that math, you end up getting 80 equals 1.16 NA, and NA therefore equals 68.96 pounds. All right. And I'm going to run out of room on this board very quickly. So if we sub 3 into 2 now, we can solve for NB pretty easily, right? So let's say subbing 3 into 2, we now get that NB equals 68.96 times 0.4, which is going to equal 27.58 pounds. So we now know NA and B, and so now what we need is, unfortunately, we don't know this angle still. So we need some equations that take into account the angle theta. Because we need to figure out what angle theta will at the point of slipping, we know NA and NB will be, oh boy, can't even, 68.96 pounds and 27.58 pounds respectively. Now we need to just find the angle that will cause that to be the case. So I'm going to erase this, but I'm going to just copy those values so that we have them. So we know NA equals 68.96 and NB equals 27.58. And I'm going to erase this so that I have room to do my sum of moments equation. This is a different board than I normally use. So now that we know that, let's look at a sum of moments. Some of the moments about, we can do any point, but I'm going to go ahead and choose point A simply because I want to. So some of the moments about point A will be 0. At point 0, we're going to get, so this weight is going to cause a negative moment of a magnitude of 80 times 7.5 cosine of theta. We don't know theta. And that is negative. And then we're going to get FB. Friction force at B is going to cause a positive. So we're going to say positive friction force B, which of course is just the same as saying NB times B sub B. So let's just go ahead and skip right to that. So friction force B is 27.58 times 0.4, and it is at a distance of 15 cosine theta. And then that's going to be positive. And then NB is going to cause also a positive moment. So it's going to be positive NB, which we know is 27.58. And that is going to be times 15 times sine of theta to get the vertical distance. So we have just those three terms. When we do simplify the math, get 0 equals negative 434.48 cosine theta. So I'm combining the like terms. So I'm combining my cosine terms, and then I'll have the sine. So when I take that value plus that value, get negative 434.48 cosine theta plus 413.793 sine of theta. And we know that the sine over the cosine, that is the same as the tangent, which is equal to 434.48 divided by 413.793. And when you take the inverse tangent of that ratio, you end up getting that theta equals 46.4 degrees. And if you wanted to be thorough, you could plug that back in, make sure that everything balances out and works out okay. So that's the second part B is probably a little bit harder than most of the stuff you'll have to do, but this sort of what we do in part A is something you'll do frequently in this unit, finding whether something's going to slip, finding what the forces will be at the point of impending motion, that sort of thing. And that's how we do it. It's all about this equation, the friction force. The maximum the friction force can be is going to be the normal force times the coefficient of static friction. So that is sort of Unit 8.1 in a nutshell. Hopefully you found that helpful. And if you have any questions, go ahead and reach out to me at any time. Thanks for watching.